Yes, so today I'll be talking about synthesizing individual and aggregate level data using a new method called multi-level network meta-regression, and in particular how we extend that to general likelihoods. So a common scenario that we often find ourselves in is one where we wish to compare multiple treatments, but they've not all been studied in the same trial. This is a common scenario, say, in health technology appraisal or assessment. A simple scenario that we might have is one where we have maybe, an A-B trial comparing treatments A and B, and an A-C trial comparing treatments A and C. And then the standard approach to compare treatments B and C would be an indirect comparison. We take the relative A-B effect and the relative A-C effect and take the difference. And the generalization of this to larger networks is known as network meta-analysis. However, all these methods make an assumption that there are no differences in any effect-modifying variables between the two study populations. They make this assumption which we call a constancy of relative effects. That is that the A-B effect in the A-B study is exactly the same as we'd expect to see in the A-C study if it had indeed included a B arm. And if this assumption is invalid, then we incur bias. So the aim of population adjustment methods is to use available individual patient data, or IPD, to adjust for any effect modifiers. Now, if we had IPD available from every study, then the gold standard approach would be an IPD meta-regression. But as I've just said, that's not actually that common. If you imagine that you're the manufacturer of one drug, you might have the IPD on your own studies, but you would not have IPD on all your competitors' studies. You'd only have published information. And so there are some quite recent methods. One is MAKE, or matching adjusted indirect comparison, which is a weighting method which takes the individuals in one IPD study here in green and reweights them into the black aggregate population. An STC, or simulated treatment comparison, is another one, and that's a regression-based approach where you fit a regression model in this study and predict outcomes into this one. Both of these methods work reasonably well, but they're actually limited to this kind of pairwise indirect comparison, this two-study scenario. And moreover, the comparisons are actually stuck in this aggregate population, which really limits their usefulness in decision-making. In larger networks, we can use methods based on meta-regression, where we fit the same model at both the individual and at the aggregate level. However, doing this incurs aggregation bias because we're fitting the same model at both levels, unless the models are strictly linear, and that's just due to Jensen's inequality. To account for this, you can split the interaction of terms into a between and a within study interaction term, but then actually you result in a model which you can't identify in a small network. So we're kind of in this situation where we don't have one method which works all the time, and there's quite a few limitations here. So more recently, we've proposed this approach called multi-level network meta-regression, or ML-NMR, snappily, I think you'll agree, which seeks to address some of these issues. First of all, it's applicable in networks of all sizes. It avoids aggregation bias by correctly relating the two levels of the model, and it can produce estimates in any given target population. And moreover, it extends the standard network meta-analysis framework, which many of us know and love, reducing to individual patient data network meta-regression if we have IPD everywhere, which is, remember, is the gold standard. And it reduces to a standard NMA if we aren't doing any adjustment, both of which are quite desirable features. And this builds on some previous approaches. Jackson et al. Used these kind of methods in an ecologic context, and Johan Janssen applied these methods to NMA, but both with some quite heavy caveats around the sorts of covariates and distributions involved. So we've taken this approach and we've generalized it, and the basic idea is, first of all, that we define an individual level regression model. Essentially, this is just an IPD network meta-regression. This is exactly what you see in an IPD meta-regression. We have some outcomes Y for individuals I in study J on treatment K, with some likelihood, and then with some link function G, we then have this linear predictor, which depends on covariates X. We have some study intercept and some regression terms here for prognostic effects, and then 4 effect modifiers, and finally a treatment effect. So this is just a standard IPD meta-regression. But then what we're going to do is we're going to average or integrate this over the aggregate populations to form the aggregate level model. And that looks like this. So we have now summary outcomes. This dot means that we've got summaries over individuals with some aggregate likelihood. And then this model now is going to be integrated over the covariate distribution, F. Now, deriving the aggregate model takes 2 steps. First of all, we need to determine the form of the aggregate likelihood, and then we need to actually do the integration. This first step is straightforward in many cases. For example, if we have normal individual outcomes, then the sum or the mean of these is still normal. And if we have binary outcomes, then we can use an approximation that the sum of these is approximately binomial. And integration, we just use a very general numerical integration approach. We use a quasi-Monte Carlo approach, which is actually highly efficient, and we use a copula to account for any correlations between covariates. So this is a very general and very efficient approach. However, problems arise with this first step, because actually it's not always easy or possible to determine what the aggregate likelihood should be. For example, if we have individual survival outcomes, what's the sum of some survival and hazard functions? Or if we have lots of ordered categorical outcomes for individuals, what should the corresponding aggregate likelihood be? So instead, what we're going to do is we're going to consider directly the likelihood contributions from each level of the model. And actually, we're going to see that we're not going to need to even work out what the aggregate likelihood necessarily is. So we start off with the individual conditional likelihood. This is exactly the same model we saw before at the individual level. And L here, capital L, those are the likelihood contributions for some set of parameters xi, which are the C's in the linear predictor, for some outcomes conditional on some covariates. And then all we do is we integrate these over the covariate distribution, over F. And you can see that now this is the likelihood contribution for an individual in study J on treatment K, but where we don't know their covariate values. It's averaged over that population. And then finally, if we multiply all these up, we get the aggregate marginal likelihood contributions. So now to apply this to a simple example, here I've simulated 2 studies, an AB study and an AC study, AB in blue and AC in gold, and 3 covariates. We've got a normal covariate, a binary covariate, and a gamma covariate. And crucially, those are imbalanced between the 2 studies. And all of these covariates are going to be both prognostic and effect modifying. I've then simulated some survival times from a Weibull model, applied 10% uniform censoring, and kind of just for fun, put different shape parameters in each of the studies as well. So the scenario we're going to find ourselves in is one where we have IPD in this study, so we have individual event and censoring times, and we know the covariate values of each individual. But then in the AC study, we're only going to have reconstructed event or censoring times, say if you digitize your Kaplan-Meier curves. And we're not going to know who these events are happening to. We're only going to know some overall summary information about that population. Now going back to the likelihoods, first of all, the individual conditional likelihoods, that's just the standard survival analysis likelihood. So we have some survival function, surviving up to time t, conditional on covariates x, and then a hazard if you experience the events, if you're not censored. And then the marginal likelihood is just this integrated over the covariate distribution once again. And that's all we need to do. It's important to note at this point that actually these survival as hazard functions, they could be of any form. They could be parametric proportional hazards or accelerated failure time. They could be splines. They could be fractional polynomials. We're not making any assumptions about the form of the model at this point. Here we're just going to fit a simple Weibull proportional hazards model. And if we do that, then we get the following predicted survival functions. And you can see that actually we're fitting the observed data pretty well, but we're also predicting, say, the effects on treatment C in the AB study and effects on treatment B in the AC study. And if we look at the log hazard ratios, first of all, if we look at those for a standard indirect comparison, so with no population adjustment, the grey vertical lines here are the truth, and in the AB study, you can see that the standard error comparison estimate of C versus A is biased, and so the C versus B estimate is also biased. And vice versa in the AC population. The B versus A estimate is incorrect, and so we have bias in the early error comparison. Using our approach, we actually eliminate that bias because we're adjusting for the effect modifiers. And you can see now we are recreating the truth for each of these. And interestingly, if we compare to a full IPD network meta-analysis, what we would do if we had all of the individual patient data, we can see we're actually not really losing any precision, despite the fact that we only had IPD from one of these studies. Moving on to a second example, here we have a network of 7 treatments for plaque psoriasis. We had 4 IPD studies in gold and 5 aggregate studies in green. And the outcomes are going to be ordered categorical responses on a PASI scale, that's Psoriasis Area and Severity Index. And there are 5 potential effect modifiers to adjust for. I should point out that there's a previous make analysis here, which we're going to compare to, and that compared treatments B and F via treatment D. But you can see that they're not accounting for the full network structure, and they're not using all of the available information. So it'll be interesting to see how well our method does in comparison. So looking at the model, I've not written it out in full for your sanity and for mine. I've got the slides at the end if you want to see. But the individual conditional likelihood is just an ordered categorical model with a probit link. And then the marginal model, all we do is we integrate over that model to get average category probabilities for each of the study arms. And then when we multiply these up, we end up with a multinomial model with average category probabilities. And when we fit that, we get these results. So first of all, here we have the results of a make. Remember, that's just treatment F versus B. And actually, that's only valid in this aggregate study population denoted with the triangle. But with our methods, we can get results from all of the treatment comparisons in the network. Here I've just got those against A, which was placebo. But actually, and we've actually reduced the uncertainty compared to the original make as well, quite substantially. And that's because we're using all of this information. But we're not stuck in just producing estimates in this aggregate population. For example, we could produce them in another one of the IPD populations. Or we could even produce them in, say, a population of interest for decision-making, such as the UK population. And finally, when we compare to a random effects network meta-analysis, we can see that actually we're really quite substantially reducing the uncertainty in the estimates. And that's because rather than averaging over all the heterogeneity, we are accounting for both within and between study heterogeneity. So in conclusion, our new methods, multi-level network meta-regression, is a flexible and general approach for synthesizing evidence from mixes of individual and aggregate level data in networks of all sizes. It's not restricted to just when we have really large networks or we have really small networks. And we've shown today that we can extend this to general likelihoods where we might not even know the correct form of the aggregate model. And this is really quite important because actually when we see these things in practice, they're often done with survival outcomes. And so it's all well and good having these models where things work when they're normal or when you've got binary outcomes, but a lot of these time in practice it's with survival outcomes. By using numerical integration, it allows for these methods to be really implemented in quite a straightforward and quite a general manner. The methods that have been worked out before by Jackson and by Janssen, they depended on having specific forms of the covariates. And if you have skew covariates or anything other than binary covariates in Janssen's case, it just broke down. You couldn't actually work this out by hand. So by using numerical integration, it really greatly enhances the applicability of this method. And finally, and this is really quite important, decision-making is really aided by the fact that we can produce estimates for a target population which is actually relevant to decision-making. And if we're saying actually that there are effect modifiers present, then actually we need to be able to produce estimates for that population. Otherwise, the estimates are totally irrelevant. We actually could reach a different decision in one population to what we would reach in another population. So actually, we do really need to be able to produce estimates in the decision target population. In terms of where we're going next with this method, there is an R package which is currently under development, and it's going to fit these models in Stan, and it will handle all of the numerical integration for you, so you don't have to worry about that. And by extension, it will also be able to fit standard network meta-analysis models with aggregate data or with individual patient data, because those are special cases. And we've also completed a comprehensive simulation study which compare these methods under a wide range of scenarios and under different failures of assumptions, and that will hopefully be published very soon. So thank you very much. Any questions?
Yes, thank you very much. I have a question. I understood that you can have a mix of individual data, aggregated data. Have you seen a situation where you really need to have individual data, otherwise you get the completely wrong answer?
Yeah, so one of the issues with this is when you don't have individual patient data, you often have to supplement that with an assumption. So actually, it's quite hard to estimate these interaction effects for the effect modification. And that's just true anywhere, not just in network meta-analysis. If you want to detect subgroup effects or interactions within a trial, I think you need maybe 8 to 20 times the sample size just to estimate that well. So if you don't have individual patient data everywhere, then you do need to potentially make some assumptions about the interactions. Maybe they're shared within treatments within a class. Maybe they're all the same for those treatments that share modes of action, for example. Yeah, so if you don't have individual patient data, or you could have lots of aggregate studies, that's the other option. So yeah, you do have to supplement sometimes a lack of data with some assumptions.
So it's very attractive having access to kind of across general likelihoods. But what's the computational cost of doing that numerical integration,
Sure.
that step within the analysis?
Yeah. So I think this example, obviously, there were only 2 studies, and we had, I think, about 1,000 individuals across the 2. And that ran in about 5 minutes, 10 minutes, just on a desktop computer. I imagine if you had a really large network of studies, because actually you're doing numerical integration for every event time in every study. But because we're using a very efficient numerical integration approach, actually the number of integration points you need is comparatively small. If you're using standard Monte Carlo integration, you might need 10,000 integration points, whereas here we might need only 100, and that really reduces the computational cost. But yeah, definitely more computationally intensive than aggregate meta-analysis, but probably comparable to full IPD meta-analysis, potentially.
Hi. Thanks for the talk. I was wondering, in the kind of comparison that you do across the various studies, so there will be some imbalance at some points. Not all studies will have been compared as many times. So to some extent, I think there might be some kind of pooling effect intervening in the fitting of the model to get the estimates of those comparisons, those differences between the efficacy of the treatments. Have you given that any thought? Do you think there is some main driver, any characteristic, be it the number of comparisons for each of the treatments or the size of the sample? Or?
I think that's a very general question just for network meta-analysis in general, not just for this approach. And I would say that's actually a strength of this method, is that where you don't have much or even any direct evidence on a treatment comparison, you can still estimate potentially quite precisely what that comparison would be by using all of this indirect evidence in the network. Of course, then you have to make assumptions about effect modifiers and all of this, which is why these methods might be quite useful. Thank you. Thank you very much.
Good afternoon. Can you hear me? Yeah. So I'm Francesco Sera. I'm from the London School of Hygiene. And here I'm presenting an extended mixed effect model for meta-analysis. This talk summarizes the first part of my PhD that I'm doing with Antonio Gasparini as a first supervisor. So I'll start with a couple of slides that introduce the topic. So this slide represents a basic standard meta-analysis problem where you have a set of studies, and for each studies you have a single effect size of measured association that is measured. And then usually there is also the assumption, that these effect size of these studies are independent. So the standard meta-analytical technique can be fixed or random effect model have the task to pool these effect size. So in the last years, I hope that you can see the graphs, there has been several extensions of meta-analysis that try to deal with more complex meta-analytical problems. Here I show some of these extensions. Perhaps the most important is the multivariate, where for each study, instead of having a single effect size, we have a set of effect size. For example, can be different outcome measures in clinical studies, or can be also different treatment effects in multi-arm trials, like in network meta-analysis. In other contexts, the effect size can have a hierarchical structure. You can think in environmental studies on which the effect size can be measured at a geographical unit that can have a natural hierarchical structure. Another important application is dose response meta-analysis, on which the effect size refer to different exposure levels, and is also not uncommon situation on which the effect size is measured several times during, for example, a clinical study. So all these extensions have a common feature, that the effect size have a correlation structure that is complex and can have, and then we need to take into account this correlation structure during the pooling process. So following the link between multi-level mixed effect model and meta-analysis, we developed this extended mixed effect model for meta-analysis that here is reported in the first equation. So this is the face of the usual linear mixed effect model. So here the vector yi represented the vector of effect size in group I. And then this model has a sum of three components. This is the fixed effect part, characterized by the design matrix, the fixed effect, and the fixed effect coefficient beta. Then there is the random terms, there is design matrix with the random terms zi and bi, this is the random terms. And then this is the within group error. So here we model the random terms following a multivariate normal distribution characterized by this covariance matrix psi I that represents the between group covariance matrix. And this is the within group error terms that is characterized by the covariance matrix S that in meta-analytical setting is usually known. So here I want to stress 2 or 3 main points. The first, that usually the analyst is interested on the fixed effect coefficient beta, that is the simple scenario that represented the pooled effects. So if, for example, you can model the design matrix with a simple intercept, so the coefficient represents the pooled effect. The other things that I want to show that under this model and this assumption, the response vector yi follow a multivariate normal distribution with covariance matrix sigma I, and this is sum of 2 components, the within group covariance matrix as a function of the between group covariance matrix. So in this case, using this approach, we can model the correlation among effect size within each group. Another things that I want to highlight here is that here I wrote the equation for the outer level group I, but in fact we can have several levels of inner group, so a multi-level structure, each characterized by its design matrix of the random terms and covariance matrix psi. This is to show the flexibility of the model that can model the correlation among effect size at multiple levels. So we are within the framework of the linear mixed effect model. So we used heavily the previous results. So from the inferential point of view, we used a profile and a restrictor likelihood approach, where we using for the fixed effect model, the maximum likelihood estimate. So the search of the parameter were restricted to the parameter that characterize the between group covariance matrix. And then we use a kind of a hybrid approach where for a certain number of iterations, we use a Eagles type algorithm to reach to approximate the maximum of the likelihood. Then we use iterative Newton-Raphson type methods as implemented in the optim procedure to get the estimates that we want. So this approach speed up quite a lot the process. And another thing that I want to highlight that we, during the computational part, we use heavily the block diagonal structure of the covariance matrices. This helps us during all the problems on the inversion of the matrix. So the analytical framework and the inferential procedure is implemented in this new package, mixed meta, that is available on CRAN. And this is the main function, mixed meta. They have several components. The main are the formula, where you can specify your fixed effect part of the model. Then there is this parameter AS that allows the user to supply the within group covariance matrix. Then there is this random parameter that allows you to specify the random part of your models. And then other important parameters are the method that at the moment is maximum likelihood or restricted maximum likelihood. And then the user can also specify a structure for the between group covariance matrix. So this is an example how you can specify. For example, this is a bivariate multi-level model. So the user can supply the two outcomes that you can think that there are two different columns in a matrix. These are the predictor for the fixed effect. Then the user can supply the within study covariance matrix. And also here, the user can specify the model from the random terms. For example, here we have two levels of grouping nested from the outer to the inner with different level of predictor for each level of grouping. To show you how to handle this kind of framework, I'll show you three examples. The first is a classical example of multi-level meta-analysis. Here, the experiment is performed at school level. So on each school, two different calendar period are compared, and a measure of standardized reading achievement is measured with positive values that show high level of reading achievement are measured. So here is how it looks like the data that the analyst can have. It's a typical longitudinal long format. And here I want to stress that the schools are nested into 11 different districts. So the matrix have a multi-level structure. So this is the multi-level meta-analysis framework. So you can specify here, we are only interested in the pooled effect. So the fixed effect is just represented by the parameter beta 0. And here the BI and BIJ represent the district effect and the school within district effects. Then here we have the two variance components, the between district and between school. And then this is the within school and nested within district error. So here you can specify this kind of model. You have just, your outcome is just the intercept that here is omitted. You can just specify the outcome. Here you supply your measure of precision. And then here in the random terms, you can specify in a kind of LME notation that the study is, in this case, the school is nested within the district. In this example, I fitted 3 different models. In the first, I performed a kind of a standard meta-analysis in which I ignore that the school are nested within district. In this second model, I just consider the district as a nesting model, nesting factor, considering the school as a repeated measurement. And here, the model that allow to explicitly model the school within a district. So here, the IC suggests that the multi-level model is the model to choose with an amount of heterogeneity between study and within school and districts. So this is a second example is an example of longitudinal meta-analysis, where here there are 17 trials on which the survival odds ratio is measured at 4 different time points. Also here you have a kind of longitudinal structure. And here you can model this mathematical problem like random intercept, random slope multi-level models. So here you have your pooled effects. Then you can model the pattern of the effect over time using a random term. And these 2 terms are linked by a covariance matrix psi. So here, I reported not just a simple linear parameterization of time, a more complex function of time, just to show you the flexibility of this approach that you can allow also to model more flexible longitudinal patterns. Here in the red curve, you have the fitted model with the confidence interval, and it is compared with the estimates that are obtained using a multivariate approach that is the classical approach that has been used in longitudinal analysis. As a last example, I'll show you what is the application that perhaps motivate this work. So we work on studying the association between temperature and mortality. And we work with a global data set with more than 600 locations, cities around the world. So this is a complex data analysis problem. So for each location, we have a data set, the daily data set of temperature and mortality. So we need to perform complex time series model to model the association between temperature and mortality. Also, the association between temperature and mortality is complex because it's characterized by non-linearity and also lagged effect. So what we usually do, we summarize the association between temperature and mortality by a set of coefficients or spline function. And then in the second step, we meta-analyze this coefficient that we obtain for each location. So this is how this framework can be used to analyze this kind of data. So here you have an object that in the row you have all the location, and in the column all the spline coefficients. Then you can have several predictors that can be the climate zone, the GDP, and the average mean temperature, or the range of the temperature. And here you have the random components where you can specify, for example, that the location is nested within countries. So this allows us to model the flexibility of the association of this is temperature, and this is the risk, and then also to obtain location-specific curves, for example, using the BLAPS prediction using this kind of models. And here in the last graphs, here you can see an example of a fixed effect, where here in blue you have the curves for a lower temperature mean, and in red for a higher temperature mean. So in conclusion, I think we defined this united framework that is complemented with software, and I think this provides a flexible tool for addressing no-start and pooling problems. So we are working mainly in 3 different directions for the next step. The first is a full implementation of the Eagles algorithm that will be speed up the computational process, especially when we have a larger number of inner level units, that we want to add, also to add additional covariance structure both in time and space. And then we want to explore better differential methods that at the moment are mainly based on a wall test for the fixed effect coefficients. So this is you can download is available on CRAN, the package Mix Meta, and this is the paper that is just been accepted in statistics medicine. So if you want more detail on these and the analytic and the examples. So thank you for the attention.
Really nice talk, thank you very much. I've got 2 very quick questions. One is, I'm very familiar with fitting multivariate meta-regression models, which have been done in the MV meta packages already in Stata and in R. Am I right in thinking this is like a generalization of a multivariate meta-regression where you allow a more general random effects structure? Is that really what's going on here?
Yeah.
Yeah?
Yeah.
Okay, that wasn't easy. Okay, and the other question is, it's also a yes. Am I still restricted to using normal approximations for these Ys? And does that become more and more of a concern as I start fitting more and more complicated models of this type?
Yeah, I think this first stage of the work, we start with the normal distribution that allows us to use, I think, to a more easy setting also for the computational procedure. I don't know if within this PhD project I have the breadth to also to go in more different distributions, but surely something that can be explored in further studies, yes. But is
Just a query on the covariance structures. There's quite a lot of work on modeling mean and covariance processes simultaneously. I'm thinking of in the longitudinal analysis setting. And I noted that you said that you wish to add in additional covariance structures. And I wondered if your method might be amenable to perhaps a data-driven longitudinal estimation method which estimated the covariance structure from the data without assuming a particular longitudinal structure.
I don't know if I get your point.
Well, let's think of just the longitudinal model first. One would think of modeling the mean process, and then the covariance structure would be a function of time.
Yeah.
So the covariance structure could be decomposed. For example, a modified Cholesky decomposition, and then you could model the diagonal of the modified Cholesky, i.e. the innovation variances, and you could model the correlation part of the matrix very simply because it turns out to be an autoregressive scheme. So that's a very easy way of getting the covariance structure without making particular assumptions.
At the moment is implementing an autoregressive structure.
Yes.
But we were thinking also in a situation where there is a kind of imbalanced time observation across
Yes.
studies. So
Yeah.
we want also to deal with this problem when the study present different time points.
There's a lot of work with by Jin Sing Pan on this area. So what I'm saying is that you don't have to make specific modeling assumptions for the longitudinal component. You should be able to estimate that from the data using Pan's techniques.
Okay.
Okay.
Okay. Thank you.
Yes. So I'm going to talk about comparison of alternative dose response analysis based on multiple summarized data. So it's very similar. It's a special case of the range of models that we have just seen. So this Francesco's presentation make my work much easier. And so I'm going to give you a little bit of background, the methods, the aim, and I perform a simulation study. So I'm going to show you some results of this simulation. So what is dose response meta-analysis? Well, dose response analysis is about getting the shape right, about the relationship between an exposure, dose, and an outcome. Meta-analysis is about combining a variety of the results obtained in different studies that they are trying to address the same research question. Dose response meta-analysis. And this is the number of publications of dose response meta-analysis over the last few years. What I did in 2005, I developed a package in data and a paper describing how to use it. So there has been an exponential increase in number of applications. Now we are talking about 150 published dose response meta-analysis, and typically those things get published in high impact factor journals and kind of influential studies. And the kind of field of applications, cancer research, cardiovascular research, public health, environmental epidemiology, nutritional research. And so there are those response meta-analyses are conducted by individual researchers or international organizations like the World Cancer Research Foundation. They continuously revise all the literature about diet and physical activity, modifiable lifestyle factors in relation to cancer. And I'm currently involved in a couple of dose response meta-analyses. One is potassium intake in relation to blood pressure in the adult population. And this is a partnership grant supported by the European Food and Safety Authority. And another example is antipsychotic drugs, second-generation antipsychotic drugs in relation to the symptoms in acute schizophrenia patients. And those two recent applications are using randomized trials where we only have a few doses that are being compared. And so I'm going to give you directly what is the structure of the data that we have. So here you have an ID for the different studies. Typically we have mean differences. So there is a zero, that's the comparison group, 2.7. So this will be the Y, the outcome variable. We have differences in means. We have standard errors, and then the dose being compared. And plus, there's also some additional information like the sample size, the standard deviation of the response variable. So this is a typical structure of the data. And so what can be noticed is that the comparison group, the difference in mean is always zero. Okay, zero here, here, and there. The reference group doesn't need to be the same for all the studies. Oftentimes, the reference group is changing across different studies. And so this is the standard error, is kind of the diagonal elements of the variance-covariance matrix. And so what the question right before my intervention was about the covariances. So the covariances is not there. So we have to reconstruct from the data to get an idea of this positive correlation between, for example, here we have two contrasts estimated using the same comparison group. So we have variances, and also the covariance is going to be positive. It's unlikely to be zero. And so what is the most common approach to analyze such a data? Well, many researchers, they're just plotting the data. You have those few data points, and then you connect the dots, and you try to guess what is the functional relationship between the dose and the response. And the typical approach is a two-stage approach. So basically, you fit a model within each study, and then you average the regression coefficients. Of course, if you want to fit a more complicated dose-response model, so you need at least a couple of regression coefficients. So it means that to fit those more complicated models, all the studies reporting just 2 doses, you have to get rid of it. So you want to combine all the available evidence on a certain topic, but because you want to get the shape right, you're throwing away a lot of studies, which is not nice. And also the typical approach is a straight line everywhere, and some researchers are fitting like restricted QB-splines to move beyond a simple straight line. So those are the most common strategies for performing dose-response meta-analysis. And oftentimes, of course, we have no idea what it could be the relationship. So there is always an alternative. There are possible candidate models. And people is looking for the smallest AIC sort of to pick up what it could be, the best model. So this is the standard approach. What we did was to propose a linear mixed effect model, similar to the one that we have seen. So we got it published a little bit earlier than Francesco. And this is a classical linear mixed effect models. I'm not using Y, I'm using, I put a hat, because we are modeling a set of empirical contrasts. So those are being already estimated based on some data. So we are modeling contrast, fixed effect, random effect, and then the usual error term. And so those models are implemented in a static command and R package. And so they're already up and running. And the only thing to notice is this. We're modeling a set of contrasts. And so if the outcome variable is a set of contrasts, also the design matrix for the fixed effect has to be centered about the comparison group. So we have to do this centering of the X variable. And so when you center X, well, within each study, you want the line to go through 0, 0, the origin. So basically, in this linear mixed effect model, there is no intercept. And then, of course, we have the random effect to capture the heterogeneity across studies. So this S, I'm using the same notation as Francesco. This is the within-study variance-covariance matrix. The variance is published, is right there. The covariance, you have to find a way to re-estimate, or simply call the principal investigator and ask for the variance-covariance matrix. That would be the easiest thing to do. Just send an email and ask for it. Otherwise, for example, we wrote a way of getting it using what's available in the paper. And there is a variety of splines. Many people is using restricted QB splines. So I'm going to focus in my simulation study. I'm going to use this type. But potentially, you could use piecewise linear, piecewise constant, any combination of different degree splines, degree 0, degree 1, and degree 3. So what is the point? So what is the point? Those response meta-analysis are likely to be published in top high-impact factor journal, are likely to be very influential. And so given the size of the data set, the kind of example that I have shown, basically really a few lines of data, but they represent thousands of patients, thousands of cases. So it's very important to be very careful when you do such analysis. So whatever you do, can you trust the results of whatever model you pick? To what extent you can push the modeling in light of this really few lines of data? So that's the question that I have. Of course, what are the chances of misleading conclusion artifacts? Imagine fitting a splines on three data points. So this is the big difference as compared to individual data. And so the aim that I had was to explore the ability of the archaic information criteria to suggest the correct functional relationship when you're using a linear mixed effect model, of the one that we have seen, for meta-analysis of summarize those response data. That's my goal. And so this is the sketch of the Monte Carlo simulations. So what I did was to generate individual data according to a certain dose-response relationship. Then I create a table. I go from individual to summarize data upon categorization of the continuous dose. Then I fit the mixed effect model that we have seen. And then I use the lowest AIC to tag the best model suggested by the smallest AIC. And then I repeat the steps a large number of times, let's say 1,000 times. And then I look at the frequency of the correctly identified dose response model. So that's the idea of the simulation. So now I'm going to give you some more details about the simulations, because I try to do a simulation study that is kind of similar to the type of data that I see. I try to use my experience to inform the simulation study. So I'm going to have a positive dose, a chi-square distribution with 5 degrees of freedom. So individual data are generated according to a simple linear function or quadratic function with a certain error term. And in terms of mechanisms generating the data, you can think of a common effect. So beta 1 is the same for all the studies, or you can sample beta 1 from a certain distribution. So if you have just a linear trend, it's going to be this. If you have a quadratic relationship, well, you sample from a multivariate normal with those means and certain variance covariances. So I generate the individual data according to those mechanisms, and then I categorize those using quantiles, true or free. So using the median or tertiles. And then I create these tables of summarized data with the mean response, differences in mean, and mean dose within each quantile. I put aside the differences in mean, the standard errors, and then sample size and sample standard deviation. That's the basic information that I need to reconstruct the covariance. That's it. So to give you an idea of the relationship, positive X, there's a linear trend. So imagine summarizing 1,000 data points into a couple of points. Just the difference. All this data becomes a difference in mean and a standard error. And this is the quadratic relationship with an increasing effect as you move along the dose. So, mixed effect model, we are going to use the smallest AIC. We are using the maximal likelihood approach. So this is the standard likelihood for mixed effect models based on summarized data. So in this marginal variance covariance, I have the within study plus the between study variability. So I'm going to simulate 10 studies, 1,000 each. And then as a kind of candidate models, I'm going to use a simple linear trend and the spline function. So this is the IDI and the dose J. This is a simple linear dose response model with a random effect in the slope. There is no intercept here. And the same thing for the splines. So 2 splines of 3 knots, the minimal amount, 3 knots, 2 spline transformation, and so 2 random effect. So those are the transformation, splines transformation. And then the AIC standard definition minus 2 times the maximized log likelihood plus 2 times the number of parameters. So P for the fixed effect and Q for the random effect. And so this is the definition of the archaic information criteria. And then as performance measure, well, I look at the proportion of simulated dose response meta-analysis for which the minimum AIC correspond to the true data generating mechanism. So PL, PS, 1,000 simulations, and let's see if you get the right response. So those are the results. So let's say the mechanism generating the data is truly a straight line. And then upon categorization, dichotomization of the dose in 2 groups, well, either common effect or random effect model, the proportion of times that the smallest AIC is telling you, okay, go for the straight line is very high. And it makes sense because if you have 2 points, you have what can you do? You just connect the two dots. Okay, that's as you would expect. Any mix of 2 or 3 doses, it's fine. If the true mechanism generating the data is a straight line, right, the ISC is doing a very good job. If the underlying dose-response relationship is quadratic, then, of course, dichotomization, there's no way that the smallest AIC is pointing the researcher into the right direction. And so, only 3%. If the mechanism is quadratic, the smallest AIC is always, is getting the right shape only 3% of the time. So it's very, very small percentages. If you have a random mix of 2 or 3 doses, this is increasing to 99%. If you want to fit a curve, you need at least 3 points. And in terms of percentage, because in many dose-response meta-analysis, there will be a mix of studies comparing 2 doses, 3. And so, to what extent you can push dose-response meta-analysis, exploring nonlinear relationship as a function of how many studies with 2 categories do we have. So you can see that I had a random mix of 2 or 3 studies. You can get even 70% of the studies with 2 doses, but you need to have some studies with at least 3 points. Okay, otherwise, the performance of the IC, is rapidly decreasing. And if you increase, I simulated dose-response meta-analysis, including 10 studies. We fit linear mixed effect model. There is some covariance between the regression coefficient. What happens if you increase the number of studies to 30? It's still the same. And then, of course, this is a picture showing you, I simulated 1,000 dose-response meta-analysis, and I just wanted to see whether, this is the difference on the y-axis. We have the differences in means as a function of the dose, using 2 as a comparison group. And it seems to be pretty good. Those 1,000 dose-response meta-analysis as compared to the truth. Even this is when we generate the data under a nonlinear relationship. So that's the true curvilinear relationship. And this is all the 1,000 estimated dose-response meta-analysis. It's kind of nice to see this agreement. So to summarize, finish, yeah. So I evaluated the performance of the IC in suggesting the right functional relationship based on dose-response meta-analysis, summarize those response data, analyzed with our linear mixed models. If the dose-response relationship underlying multiple studies linear, well, the AIC is very good in suggesting linearity, even if all the studies categorize the dose in two groups. If the dose-response relationship underlying multiple studies is nonlinear quadratic, the AIC is very bad in suggesting nonlinearity when all the studies categorize the dose into 2 quantiles. In such a case, of course, any random mix of 2 or 3 doses will substantially increase the performance of the AIC. And in this simulation, I didn't see that much of a difference simulating under a common effect or random effect mechanism. Thank you very much.
Can I ask a general question about meta-analysis? I feel meta-analysis is quite a good way to look at the research compared to, you just focus on one research. But my question is, because from last talk and your talk, the criteria you include the research, the number of research in the meta-analysis is various. And the last talk, I heard about number about 56 and 17, and your talk is mentioned about you include the research about 5 and 10. So is there any criteria how to select the research to include in your meta-analysis? Because normally a statistic test is the more sample and the more powerful and the more convincing result. So I just wonder, is there any criteria to include the research?
As far as I know, there are no criteria. This international organization, you want to get, what is the state of the art? What do we know about the relationship between this exposure and this outcome now? And so there is a group of people going out and collecting all these studies, and they try to collect typically there is a protocol. So this is the analysis stage. Of course, this is the statistical analysis. So the question is, how do you get there? How do you put together the data set? Typically, there is you identify exposure, disease, how has to be measured. So there is a protocol, and then you try to collect as many studies you can find in any sorts.
For example, if there is research, you don't like the result, but it's really fit, this kind of research setting, will you exclude that research? Or you include every research you can find?
But yeah, that's very common, to any model, So I guess so the question is, what happens if you don't like the results? Well, you do as you would do with any other thing, So in this sense, dose response meta-analysis is simple linear regression model with some weights. So, you have to be careful. You have to think about the mechanisms generating the data and the inclusion of the studies. Of course, deciding what to publish based on what I see is bad practice, whatever you do, So, but I understand the point, how the selection of the studies is there. In this sense, I agree. Yeah.
A comment and a question. Relating to the previous question, there's this business, which I'm sure many people are familiar with, the Cochrane collaboration. There's a whole literature on appropriate selection of studies for meta-analyses and wrong ways to do it. So if you want to be fussy, there's plenty of guidance on that.
Yeah.
But relating to your talk, my recollection is that there's a problem with applying AIC and BIC to mixed models, that if you're trying to assess random effects, then you must keep the fixed part of the model the same, so as to keep the constant in the likelihood function the same. Okay. I appreciate that's not, you're almost trying to do the opposite. You're looking at the fixed part of the model, but does this business of whether the AIC is actually working to compare models, does that have any impact on your work?
Yes, I see the point. I use maximal likelihood, and I'm using, so of course, you can also use restricted maximal likelihood, but you have to be very careful when you do those things. It seems that maximal likelihood should be fine to compare those two models. They're nested because the restricted cube splines. If you fix beta 2 equal to 0, one variance of beta 2 and the covariance beta 1, beta 2 equal to 0, then you get back to the simple linear function. So the two models, the candidate models, were nested.
I think they're nested. That absolutely answers my question.
And I use maximal likelihood. If you use the smallest AIC based on the restricted maximal likelihood, it would be completely off, for example. So this is something that I noticed, that the estimation method makes a big difference.
Thanks.
Could we thank all three of our speakers for 3 great talks?